Our third postulate of quantum mechanics relates again to the intersection of operators and wave functions. So if we have an operator A, it's our favorite operator. If we want generic operator is what we like to call it. The only values of the observable that corresponds to that operator A, which we'll call little a, right? So this could be, say, position or momentum or energy. So the only values that will be observed are the eigenvalues. We'll call them A sub n because there could be more than one of them that satisfy the eigenvalue equation which would be the operator A operating on our wave functions, psi n, give the eigenvalues, and again, our wave function again. So for our operator, this eigenvalue equation becomes the way that we know what possible values of A that we can observe. And this is a big difference between quantum mechanics and classical mechanics. In classical mechanics, there's no sort of limit on what your values observable can have. There's anything that's reasonable. So for example, for position, you can have any possible position, right, from negative infinity to positive infinity, as long as it satisfies the boundaries of your system. In quantum mechanics, that's not true. So for example, for energies, as we saw with the particle in a box, there are only specific energy levels that are allowed, and those are those that satisfy the eigenvalue equation, and you can't have something in between. And that's very different from what our normal everyday life, what we're used to, right? We can say move a ball, half a centimeter or whole centimeter or quarter of a centimeter, right? There's no limit to like what sort of distances we can move things or how much energy we can give it. But for molecules and electrons and atoms, that's not true. They can only, you can only observe the things that satisfy these eigenvalue equations. Now, this is sort of a corollary that went with postulate 2 and kind of relates to this one, is that if we have a degenerate system, and just as a reminder, something being degenerate means that you have multiple wave functions that give you the same eigenvalue, multiple eigenfunctions that give the same eigenvalue. So for example, we have operator A acting on wave function 1, gives us our observable A, and gives phi 1 again. But we have a different wave function, phi 2, that gives the exact same value, right? So this would be a degenerate system where we get the same A from both wave functions. Right, so if we have something like this, there's a corollary that any linear combination of our two wave functions, phi 1 and phi 2, is also an eigenfunction of the operator. So what that means, let's kind of show that that's true and kind of what we mean by that. So some linear combination would look something like this, where we have some constant. A linear combination is we can take some constant, make that clear, it's C, C1 times our wave function 1, C2 times wave function 2. And C here can be positive, negative, it can be complex, even be complex numbers, but it's a number, right? It's a constant. This is a way of combining phi 1 and phi 2. If we take our operator and act it on this linear combination, in quantum mechanics, all of the operators that we work with are linear operators, meaning that we can distribute it here. And so it satisfies this property. We can take C1 A times phi 1 plus C2 A times phi 2. But we know by definition of the fact that phi 1 and phi 2 are eigenfunctions that we'll just get C1 times A times phi 1 plus C2 times A times phi 2 where this is the eigenvalue. And now we can factor out this eigenvalue a, and we'll get c1 phi 1 plus c2 phi 2. Well, we just got another eigenvalue equation, right? So we have our function we started with, we end up with it again. This combination is also an eigenfunction. And this is a consequence of the fact that all of our operators that we deal with in quantum mechanics are linear operators. And so if we find a solution where we have degenerate states, we can kind of combine them however we want, and those eigenfunctions are still going to be, those linear combinations are still going to be eigenfunctions.